All right, so example 10, it's not often we get to learn about a new parent function, but today is one of those days, right? And it just happens to be National Hot Dog Day. That is a total coincidence, for whatever that means. Okay, so there we go. Try to get my pen. It's not working. All right, sketch the graph of this guy. This is the absolute value of x over x, which, believe it or not, is equivalent to x over the absolute value of x. And it's not 1, believe it or not. So here's how we're going to do it. We're going to decompose the function into a piecewise function because there's a couple of ways we can handle absolute value of x. First of all, the absolute value of x sometimes can be written like this. This is an identity. And when we get to derivatives, we might use that method. The squared has to be under the radical by order of operations. That's exactly the same thing. But there's another way, and that's what we're going to do right now. We can decompose the absolute value based upon the sign of x. So here's what we're going to do. We're going to say that f of x, which is the absolute value of x over x, that's just the version I choose to write, it's equal to, and then we'll put kind of an open brace. So let's think about the numerator. First of all, if the thing inside the absolute values is already positive, you would make it positive simply by just dropping the absolute values. So that's going to be x over x, which now we can simplify to 1, and then we have to say when that happens. So when is x positive? When x is what? In relation to 0. Greater than, yeah. So we're basically saying here, it's kind of like writing a little computer program. If you start on the right, if x is greater than 0, then the absolute value of x is just x. And of course, then that would simplify to 1. Else, otherwise, you can come down here, if x is less than 0, namely negative, how would you manually make a negative value positive? Well, without taking the absolute value, we're trying to write a program that would basically apply the absolute value. Oh, you could square it and then take the square root of it. That would work. Someone said break the negative sign off with your hand. Or how about just multiply it by -1? Would that work? If you have a -5 and you want to make it positive, just multiply it by -1. That's probably the easiest way. So I'm just going to say it's the opposite of x. How about that? Over x. So if x is a negative number, we're going to make it positive by taking the opposite of it. Okay? And that's going to then equal -1. Now, what about if x is 0? I haven't included that in the piecewise definition. Can x equal 0? For the absolute value function itself, it can, but because we're dividing by x, x can't be 0, so we're not going to define it there. And so what we basically have, if you want to simplify this, we get it down to this nice function. It's going to be 1 when x is positive, and it's going to be -1 when x is negative. Okay? That is what that function looks like. So what would that graph as? Well, I'll show you. Pretty easy. There's a y-axis. There's an x-axis. Here is 1. And here is -1. So when x is positive, it's going to be the line y equals 1. And when x is negative, it's going to be the line x equals -1. And, of course, it's undefined at 0, so we put open circles there. Okay? What type of discontinuity do we have at 0? Based on the graph, there's a jump, right? So this is the one exception. Remember I said 99 times out of 100, when direct substitution gives you 0 over 0, it's a whole. This is the one exception where 0 over 0 actually gives you a jump, okay? And it's because it's a piecewise function in disguise. So because of that, I've given a name to this parent function, the absolute value of x over x, which looks like this. I call him, from all the years of growing up watching Dora, and by growing up, I mean like in my early 20s, growing up with my son and daughter watching Dora the Explorer, right? I'm going to name this graph Senor Salta, okay? That translates to what? No offense to Michael Jordan. Jumpman, right? So this is the Jumpman graph, or Senor Salta. In Colombia, incidentally, I've had some Colombian students. They said they wouldn't call him Senor Salta. Jumpman is known as the following, so we'll get a multicultural lesson here. Hombre trepador, okay? So I don't care what you call him, Senor Salta, Hombre trepador, or just Jumpman, okay? It's the absolute value of x over x. And notice when you plug in a 0 for x, you do get 0 over 0, and that's the jump. Okay, now, what we are going to do is come up with a way to cleverly evaluate limits of Jumpman on either side of the jump, okay? Which should be pretty easy. If you know where the jump is always going to be at the x value that causes 0 over 0. But notice on either side of the jump, it's going to be either the same positive number or the opposite of that number, depending on which side you're on in the sign of the equation, okay? So the function value is a constant. So everywhere to the right, the limit value and the constant value are the same, and everywhere to the left, the limit value and the constant value are the same. So if we wanted to figure this out, the limit as x goes to 0 from the left of that function, well, if you know what the graph looks like, right? From the left of 0, hop on the graph, start heading back towards 0, we're approaching what? -1. Okay, so here's how we're going to do it. We don't have to memorize the graph, and we're going to have some pretty intricate transformations of this graph. If you try direct substitution, right, never not first, you're going to get 0 over 0, correct? You're going to identify Jumpman. It's going to be pretty easy to spot because he has those absolute values over itself. So it's the absolute value of blob over blob. It doesn't always have to be x. Or, of course, it could be flipped. It could be blob over the absolute value of blob. If you're approaching something that looks like that, it's a quotient where one of them has absolute values, and you're getting 0 over 0, we're going to use the fact that it's always going to be the same y value everywhere to the left of the jump. And so here's how we evaluate it. If we're approaching 0 from the left, pick a number to the left of 0, any number to the left of 0. -1, okay? And then by direct substitution, what do you get when you plug a -1 into the equation? You get the absolute value of -1 over -1, which is 1 over -1, which is what? -1. What if you don't want to plug in -1? What if you like -11? Okay, that's -11 over -11. The absolute value of -11 is 11 over -11. It's still -1, right? So that's what's unique to Jumpman. Because it's horizontal line segments, you can choose any number from the left or right to evaluate the left or right-sided limit. And that value will end up being the limit value, okay? So what would be then the limit from the right of 0? Yeah, if you know what the graph looks like, it's 1, but let's try it the other way. I plug in and I get 0 over 0, so I know that this is the x value where there's the jump. And so I can pick any value to the right of 0, like I'll use 8675309. All over 8675309. And of course, the absolute value of that is 8675309. 8675309. I've got it. It equals 1. Yeah, you're right. Yeah, that's it. It's 1. See, I probably could have chosen something different, like I don't know, 1, 2, something like that. So that's how we handle Jumpman, all right? Now, what would the general limit be? Based upon the definition of a limit. DNE, good. Remember, the general limit theorem says that the general limit only exists if the two one-sided limits both exist, or finite values, and are the same. And they are not the same, okay? It's 1 from one side and -1 from the other, so the general limit doesn't exist. So here's another thing. If you have a general limit, and you can identify Jumpman, and you're approaching the value that gives you 0 over 0, you know it's going to be DNE every time. You know there's going to be a jump. If it's a one-sided limit, we have this trick of picking a value on either side. Okay? But you can't get too excited. What if you see a general limit, the limit as x goes to 3, and you're like, hola, señor Salta. And you're like, it's a general limit, it's DNE, órale. Is that right? No. Because never not first. Primero siempre. What? Direct sub. So if you plug in the 3, you get the absolute value of 3 over 3, which is solo uno. Right? It's 1. So try not to overgeneralize. It's easy to get excited, right? You recognize functions, but really it depends on the value you're approaching. It's only if you're approaching 0 over 0 that it's going to be that jump location. Okay? So that's pretty easy. Could they get more interesting than that? Yeah, see. Evaluate the following. Okay, oh boy, look at that. We got the limit as x goes to 5 from the left. I've got an absolute value of a linear function over a linear function. That kind of looks salty, doesn't it? Or jumpy. Let's try direct substitution. You plug in a 5 and you get 10 minus 10, that's 0. Over 5 minus 5 is 0. So here's what we know. This is actually a transformation of Jumpman. And let me show you why you're not going to have to do what I'm about to show you every time. You're not going to have to do this. Let's think about the function. absolute value of 2x minus 10 all over x minus 5. This is a transformation of Jumpman, okay? Let's put it into standard transformation form. I can factor a positive 2 out of the absolute values, and I can pull it out front. That's going to leave an absolute value of x minus 5 all over x minus 5, okay? So let's think about what that does to Jumpman. First of all, what does multiplying any function by 2 do to its graph? If you have 2x squared versus 1x squared, the 2 is a vertical stretch, right, by a factor of 2. The y values are twice as big. So now instead of 1 and negative 1, it's 2 and negative 2. And what does replacing x with x minus 5 do to any function? Shifts it to the right. So if the jump used to be at 0, now that jump is at 5, and the graph looks like this and like that. Now you could put it into standard transformation form and sketch it, but again, notice on either side of 5 where the jump is, the function value and the limit value are the same. So I know that the answer now, because I've sketched it from the left of 5, is negative 2. But here's all you really need. All you need is the absolute value of a linear function over a linear function. It doesn't even have to be the same. Or, of course, they could be flipped. If you get 0 over 0, that's the jump location, okay? The other rest is just a transformation. So we could use our same method. Pick a value that is left of 5. 4, okay? Let's plug in a 4. Absolute value of 2 times 4 is 8 minus 10 all over 4 minus 5. That ends up being the absolute value of negative 2, which is 2 over 4 minus 5 is negative 1, and it ends up being negative 2, okay? If you would have chosen 0, you get the same thing. So for the Jumpman, and this is how you identify transformations of the Jumpman, absolute value of linear over linear or linear over absolute value of linear. You don't have to bother getting them to match up with x minus 5. You can leave that coefficient of 2 inside the absolute values. Just recognize if you get 0 over 0 and it's a one-sided limit, you can use the trick of choosing any value, okay? So try that out right here. Pretend you didn't know what the y value was, because there are always going to be some metrics. So if it's negative 2 on one side, it'll be positive 2 on the other. But verify for yourself. Direct substitution first. All right, I use direct substitution first. Absolute value linear over linear, I got 0 over 0. So I know it's the jump location. I'm approaching from the right of 5. So I chose 10. 10 is to the right of 5. I plugged it in, evaluated, I got 2. You chose a different number than 10 more than likely, hopefully. If not, you get the same answer I get either way. You get a 2. And that's the right-sided limit, okay? Same thing here. You got the limit, direct sub, you get 0 over 0. In this case, if you recognize absolute value of linear over linear as Jumpman's transformation, and you're approaching the value of the jump, the limit is what in general? D, N, E. Yeah, you know that right away without even having to bother about sketching it. So you really don't have to know what the graph of Jumpman looks like, but you do need to recognize it, okay? So those are standalone problems, and these are probably what you'd see on my test or the AP exam. But we can use the properties of limits from section 1.2 to answer questions such as this one. So on your own, on your lonesome, go ahead and do this one. I want to see what you get. I just saw another notation. Just in general, if you're like squaring a -4, make sure, and you recovered, make sure you have parentheses around the -4. You called it positive 16, but you would lose points on like a short answer if that wasn't in parentheses. Anybody want to volunteer an answer? Anyone brave enough? You're all brave enough. -8, I actually saw in a couple. 25 halves, there's another -8. There's a +8, there's another -8. There's another -8, another -8, another -8. Not quite a -8. Again, with the democracy of math, the -8s win. I guess that's the answer. That's how it works, right? Nope, it's not how it works. So let's see. It might be -8. Never not first, right? Direct sub. If you plug in a -3 for x, you're going to get, I'll do it up here, you're going to get 9 times the absolute value of 0 is 0 over -12 plus 12 is 0. So, of course, that is 0 over 0. Okay, sweet. Now, notice you got an x squared up there, but here's the part that's important. You do have the absolute value of a linear function over a linear function. And what was causing the 0? Was the x squared causing the 0? No, it was this tandem that was causing the 0 over 0. That's Jumpman right there, okay? And he has now, I guess, a partner in crime, x squared, that's going along with him. So to evaluate the Jumpman piece, we know that we could choose a value to the left of -3. And most of y'all chose -4. So let's see what that would look like. If you plug in a -4, you get -8 plus 6. Although -4 times 4 is -16 plus 12. And remember, when you plug in, you don't need to write the limit anymore. So that's going to be the absolute value of -2, which is 2, all over -16 plus 12 is -4. That gives you -1/2. Well, what else do we have there? We have x squared. So I saw some of y'all go ahead and say, all right, I plugged in a -4, so I'm going to go ahead and say -4 squared, which is positive 16, which then half of 16 is 8, so it's -8. And that would be a great answer choice on a multiple choice question on a test. But is that right? No, and here's why. If you plug in a -4 to x squared, you're finding its limit value at what? Not -3, but at -4 or 4. That little trick only works on the Jumpman piece, only on the Jumpman piece. So if you use the properties of limits from 1.2, that basically says the limit as x goes to c of f of x times g of x is equal to the limit as x goes to c of f of x times the limit as x goes to c of g of x. The limit of a product is the product of the limits. You can actually break it down into two problems. You find the Jumpman piece, -3 from the left, and I'll write that first. That's the absolute value of 2x plus 6 all over 4x plus 12. Sorry, that's the Jumpman piece. That's the linear over linear. That's the 0 over 0. And then times the limit as x goes to -3 from the left of our old friend x squared. And the beauty of this property is that you can evaluate those each independently as if they were two separate problems. How would we evaluate this piece and this piece alone? Plug in a value less than -3, like -4. And that's going to give you a -1/2. Well, I won't do all the work again. But then how do I evaluate this limit? I don't plug in a -4, right? What have we been doing? I plug in a -3, and I get +9. So the answer, the real answer, is -9/2 or -4.5. Okay? So you might have combinations there with other functions and Jumpman. If you can isolate the Jumpman, that is the only piece that you can then plug in any number left or right. All the other pieces you have to evaluate like we've been doing previously. Try direct substitution again. All right? And it's a real common mistake to plug that number into both pieces. So that would be an answer choice. All right? Now, you don't have to physically write it like this every time. If you just isolate the Jumpman piece, say, okay, that's what I'm plugging my -4 into, but everything else I'm just going to plug in a -3. Okay? So try that on this one. Letter B. Let me see your work. Well, yeah, you could pull the 2 out and the 4 out. There's really no need to do that. Yeah, that's fine. That's fine. That's just doing extra work. And then you get a 1 there. Yeah, that'll work. Yeah, versus just leaving the 2 factored in and the 4 factored in, evaluating x squared and calling it 9, and then just plugging in your like negative whatever you plugged in here. You can just plug it into here. So what it does is it saves a line of writing, because remember, if you're writing it like on the short answer, see on your second step you have your x's still. If you don't have your limit in front there, then you're going to lose a point. So you could probably go straight to, okay, 0 over 0 is caused by these. I'm going to go straight to my answer. Plug in a negative 3 for x squared, you get 9. And then plug in whatever you did, a negative 4. So you get negative 8 plus 6 is negative 2. Absolute value is 2. And then negative 4 times 4 is 16 plus 12 is negative 4. And then you can evaluate that. But if you want to factor those linear factors, that's perfectly fine. As long as it's linear, it's of the form mx plus b, you're good. Okay? Yeah. Uh-huh. Yeah, you did it right. Just watch that notation. Probably practice it. Okay, so if you plug in here, you do get 0 over 0. Now, here's what you want to notice. In the bottom, you do have the absolute value of the linear function. There is not a visible linear factor in the top, but because it's a quadratic, and we've already seen this with quadratics with our factor and divide out method, you know that because it's a quadratic and you plugged in a 6 to get 0, that x minus 6 is a factor in there, right? Because it caused a 0. And that's going to be the linear guy that's going to be then associated with my absolute value downstairs. So in this case, you do have to factor it, because you need to associate that linear factor causing a 0 with the denominator, which is causing 0. So if we factor the top, that's going to be, of course, an x minus 6, and then the other factor here is going to be an x minus 2. Now, if you want, you could just put this piece over the absolute value of 2x minus 12, and then this piece, you could just say it's over 1, because it's the associative property of multiplication. Now, what Kevin was doing earlier, which is totally fine, if you want, you could factor the 2 out of there. There's nothing wrong with that. You'll just have a 1/2 lingering around, which will become part of your answer. But as long as it's a linear function of the form mx plus b, you can leave it, okay? So now when you plug in, you still get 0 over 0, but this is the piece causing the zeros, right? And that's the Jumpman piece. So how would I evaluate something like that without graphing it? Plug in a 7. A 7 is great. It's greater than 6. So 7 minus 6 is 1. And on the bottom, 7 times 2 is 14. 14 minus 12 is 2. The absolute value is 2 is 2. There you go. So that's a 1/2. What do I then plug into x minus 2? A 7? No, 6. A 6, right? I treat it as an entirely separate thing. I don't want to rewrite it with the limit in front. That's just too much writing. I got to plug in a 6. 6 minus 2 is 4. And so your answer is half of 4, which is 2. If you would have plugged in a 7, you would have got 7/2, and that would make a great answer choice. So identify the Jumpman piece. Linear over linear, 0 over 0, okay? And then evaluate everything else the other way. All right, last one here. We'll do this together. If you plug in, you get sine of 7 times 0, which is 0, over 49 minus 49, which is 0. Right? So I do get 0 over 0. Notice now we have the Jumpman piece, part of it, in the top. It's the absolute value of a linear function. When I plugged the 7 into the bottom and got 0 into that polynomial, it's because there's an x minus 7 factor there, right? So it's very similar to the first one. Sine of x is just kind of an innocent bystander. When you plug in a 7 into sine, you get sine of 7, which is just some number. So let's go ahead and factor this one as well. We'll get sine of x times the absolute value of 3x minus 21. And again, I'm leaving the 3 in there. And then over here, I'm going to get an x minus 7 times an x plus 7. And the reason I wrote it like that is because now if I associate those two together, linear over linear, that's what's causing 0 over 0. Okay? That's what's causing 0 over 0. So into that piece, I can plug a what? Am I approaching from the left or from the right? Both. So what do I know about this? Yeah, I'm going to get sine of 7 over 14 times dne. Guess what that makes the whole thing? dne, right. Because it's a general limit at the location of the jump. But again, if this had been from the right or from the left, then you would plug in that number only into the boxed piece, and then you would leave it as the other piece, sine of 7, which is an exact answer, over 14. Okay? So isolate the linear over linear. Only one of them has to have the absolute value. It's either the top or the bottom. And then you can use that little trick. All right, that's it. Tomorrow we'll get into sine and cosine. There's some things we have to memorize, and then some kind of last method of general cleverness. So we should be able to finish this tomorrow. Maybe a short little quiz tomorrow. Maybe just a short one. Like maybe we did Ratcon again today, lick 'em over lick 'em, and sledgehammer. So maybe one of those. All right. Have a great rest of the afternoon.